I'm Brandon Moore, here from Pi², here to talk about our work on cryptographic proofs of mathematical proofs. So I guess a little bit about why we want to do this, and it's kind of the whole company. The Pi² is proof of proof. But some mathematical proofs, they're flexible. You have kind of a single fixed logic that works for all sorts of applications. And we're particularly interested in proving things about programs according to a language definition, formal verification of security. You can even just prove the result of a concrete execution if you can do that efficiently enough. So then you end up with a very small trust base, just the language definition and a simple proof checker that doesn't change for the different languages, no compilers or interpreters or whatever. But then on the other hand, using a SNARK gives you, a very small proof, pretty fast to check. And I say ZK or ZK SNARK or SNARK. A lot of the times we don't care too much about the ZK part or the proof of knowledge part if you just want to know that something is true, that your contract is formally verifiable. Just knowing that there exists some proof is as good as knowing that the prover actually knew it. And also leaking the details might not matter. But there are also other applications like, if you're trying to use this to encapsulate actual concrete execution and there's maybe secret input. So yeah, SNARK is fine some of the times. But then this talk is not about the big picture there. It's about how exactly we prove our mathematical proofs. So your first thought might just be, hey, run a proof checker in a ZK VM. You compile whatever. Well, you can do it, but it's very slow. You might even run out of guessed VM. So we tried to design something to more directly use the capabilities of the SNARK proof system to check the proofs and also adjust the design of the proof language itself to be more easily provable. So here's an example of the kind of proof we're talking about. Yeah. So, sort of derivation you see, and there's all these proof rules. So this is just sort of a propositional logic with a little bit of complexity. The idea is that these are like meta variables that can be substituted with terms. So we have a little more going on. You may have seen this in something like MetaMath. So you have modus ponens for applying implications. Substitution step, the idea is that instantiates meta variables, and then here's these propositional axioms you may have seen. I named them after the S and K combinators because that's the only way I can remember to prove anything with them. But so here's like a tree structured proof. Another format that you might see is a Hilbert proof, where sort of each step is a proof rule. Usually you just write down what you proved and what earlier steps you used. And so in both of these cases, we saw the same general structure that there's some set of proof rules. The proof is a bunch of instances of these proof rules. So you need to check that it's locally, actually shaped like an instance of the rule you say it is, and then also check that all of the hypotheses are satisfied by the conclusions of another step. And also, it's maybe sort of implicit in both of these, but you need to make sure that this is like an acyclic graph. Of which proof satisfied which other one. Yeah, so here's maybe the proof rules that we've used so far. So if we're being a little more careful, we would say that the proof rules can have parameters like this. A and B terms are the modus ponens that get substituted in. The rules can have hypotheses and conclusions. And in general, the hypotheses or conclusions might be different kinds of statements, but here the only thing we've got going on is we're saying, okay, this is proved. This term is a true proof. The axioms, and then, but we also have the substitution operation that can just instantiate it with the substitution, and that function application thing is not really a term. And ordinarily, pen and paper proofs or even automated proof assistance, it's fine to have things like that, but. For our case, we think a little bit more, what happens if you were consider trying to run it on a ZK VM or more generally have a ZK circuit? Well, every little instruction that goes into doing the function application gets materialized onto the transcript and takes up space. So in a conventional setting, leaving any easily computable, decidably checkable things out of a proof format, it's good. It saves you disk space and stuff, and you can recompute it quicker than you can read the bytes from disk, maybe. But then in a ZKVM, everything shows up in the transcript. All the intermediate terms you compute into memory show up in the transcript. So the first kind of thought here is, okay, don't try to hide these things. Just, you can give everything up front, give it as part of the proof file. If it saves you more work recomputing it than it took up in space, then you come out ahead. So, and then also if it's a term that would have been computed at runtime, referring to that term up front doesn't cost you anything. So we can say the substitution rule, one of the parameters is okay what the result is. And now you're checking as a hypothesis that this substitution comes out. And then it's a similar story for computing the substitution itself. Maybe some things, arithmetic, maybe crypto things, you can come up with a super efficient ZK circuit for proving that specific thing, but for something like recursing over a term, well, certainly, again, in your ZKVM execution, you just have the whole computation tree would become laid out on the transcript anyways. And as far as I know, if you're designing a more direct circuit, you get the same sort of thing. So at least for recursive stuff, you might also just say, instead of having some notion of executable functions, just let's define things with more proof rules. Also, if the execution ever had to do tests, make choices, backtrack, that's all just more wasted work. You can just tell it to do the right thing from the beginning, supply it as advice to the ZK computation, whatever. So kind of the first thing is say remove any functions and just make them more hypotheses. So I said there were only two relations. Well, now we've got a third relation here saying that, hey, we've got a second relation saying that the result of this substitution is this. And then if you start thinking what the rules would look like, say that you're substituting a term that's an implication, you need to figure out what the substitution of the subterms is. You make a substitution into a variable, and then, hey, we've got this new judgment for looking up a single variable. So we've got a few relations running around. It's not, the details of what exactly they are isn't that interesting, just that in general for a proof system, especially a proof system about a programming language, you might have a lot of relations. You might have a type checking judgment, you might have memory lookups, you might have stack things, and then all sorts of auxiliary functions too. But it still fits into the same notion. You have hypotheses and conclusions. You make sure that your hypothesis is the conclusion of some other step, including being in the right kind of relation. So now we talked already a little bit about what ZKVM can do efficiently, but now we need to think a little more about what these SNARK proof systems support. So I'm going to talk in very high generality here, and this is also kind of how we thought of them. But in the high generality, there's some witness that you're proving satisfies some constraints or some problem. The witness is always made up of a bunch of numbers from a finite field, usually primes, although the Arrhenius people use towers. And then your basic, the sort of primitive constraints that you can just put down freely are some kind of low degree polynomial, or even slightly more restricted in the rank 1 constraint systems, but low degree polynomials over a small fixed number of variables. And then the main thing that lets you do any sort of global collective operation are permutation and lookup arguments. And if anybody can suggest a third global operation I'm missing out, we'd certainly want to see if that's something we can put to use. But yeah, so the exact realization of this is a bit different. In the Stark, Plonkish kinds of things, your witnesses are arranged in a two-dimensional table, and your polynomials are checked between each pair of rows, so it kind of has this uniformity. The rank 1 constraint system, they're just in a vector and have arbitrary matrices. And then you can think about general arithmetic circuits, compile them to one or the other, maybe even think about like a GKR circuit evaluation. But in all these cases, the basic things you've got going on are simple addition, multiplication, constants over a finite field. And also really built on top of that math is the permutations and lookups. This kind of seemed to be the common denominator. Just to, recall the functionality. So both of these are things you sort of build into the constraints or circuits when you're setting up the instance. So you pick two lists of the witness elements. I guess I'll say in like a SNARK, they might need to be like two complete columns of the table or something, or segments. But anyways, given those two lists, so the permutation argument is just a way of enforcing that one list is a permutation of the other. The lookup argument lets you enforce that the set of values in one list is a subset of the set of values in the other. And it's maybe easier, maybe you can use permutations to get like a multi-set thing, but we really want a set, so you can look it up with more times in the A's than it was in the B's. Like you can use the conclusion of a proof step in a bunch of later steps. So anyways, you can do these things. They also generalize very easily to having the list be lists of like a fixed size, say 3 tuples of field elements. And then internally it's, computes some sort of polynomial expression incrementally, and then, they only come out equal if the things work. But yes, I guess I said I'm not going into the implementation yet. And then the also key trick with permutation, usually the way that you use the permutation for anything really interesting is you use it to make a sorted copy of a list that's sorted by something else that makes the check that you want to do local. Important thing, ZKVM, like the memory arguments, they have this kind of linear instruction stream with the read and write operations, and you need to look back many instructions to see, okay, where's this value that I'm reading coming from? But then they emit these tuples of the address and something like the cycle count and the values, and then by making a copy of that that's sorted first by the address and then by the cycle time, then everything's the nearest neighbor. That's how we'll be applying permutation arguments. Right, so with that review of what the SNARK systems give us, and we can think how this kind of matches with what we've got going on with the proofs. So the local shape of the proof rule, the hypotheses and conclusions of the individual rule are, for the most part, just like simple expressions involving the parameters. Also, I guess, because we said that we're not going to allow you to have complicated functions like a substitution going on, really that's also not there. And then the non-local check that you're doing is checking that the hypotheses of your proof step are satisfied. So filling out the exact form of the hypotheses and conclusions given the parameters, just local fixed relationship. So probably we can use the local constraints for that. And then we would really like to use the lookup arguments for the hypotheses. But there's a few problems with that. So one is that it's just checking the subset. There's no notion of order. Like the Hilbert proof was only supposed to refer to earlier proof steps. The more tree-structured proof was supposed to be acyclic, so it doesn't do that. Also, the lookup only works over field elements, and we've got all these expressions running around. So we can address both of these things by changing the form of our rules and, I guess, a little more functionality. So the general strategy, we can enforce that things are not cyclic directly in the rules by kind of adding a depth counter where necessary and having explicit inequalities. So then the proof checking can try to match them up freely, but the inequalities will break any cycles. And then replacing the terms with numbers. So generally the idea is to just, kind of arbitrarily assign numbers to terms, just like you might arbitrarily have, say, a memory address that the term got allocated at, or some index into a table, but there's a little more complexity there. So yeah, here's the idea for how we can prevent there from being cyclic proofs, even if that's not directly enforced by the lookup. So you just add this extra argument, which is interpreted as the depth, and then add some inequalities saying that the depth of your hypotheses, to the extent that they need to carry depth, are less than the depth of your conclusion. I think the inequality is cheaper than specifically taking the max, and as long as we break the cycles, it's good there. Yeah, I guess other comment is that yes, it's kind of messy, fairly mechanical. You might imagine some sort of translator that sticks these in automatically, and I'm going to put these aside for a little bit, but so you need to modify your proof system to include these also. So right, the hypotheses and conclusions. I guess the first step is these the entire claim. Like we said, say this substitution comes out, or this term has been proved. Feeding those into the lookup argument. Well, it's really the expressions that are the problem. If those become numbers, then there are already these relations that are just taking a fixed number of arguments. So you can just assign a different constant to the different relations, pack them all into a single tuple, pad it with trailing zeros. The zeros can even be free depending on the back end. So now we've got all the kinds of claims we're dealing with, in a form lookup likes it, presuming we can handle the terms. And this is maybe not as bad as it sounds, because if you think about what just a efficient conventional program for doing proof checking is, well, it would already be dealing with the terms with some sort of sharing preserving representation. Maybe it's pointers, possibly it's table offsets, but there's already some number. And you even have this structure that the pointer or the table entry is like one constructor of the term. Maybe it says, hey, I'm an implication, here's my children, and again, numbers for the children. And then the sort of thing that your code does to handle the part of the proof rule that had an expression in the hypotheses or conclusions, sort of taking this term and walking step by step down the constructors of the term to make sure it matches another one or has the right shape or whatever. Yeah, and as before, we are assuming that everything is sort of provided in advance, so you don't need to know how to guess what the implication between these two terms is given their number. You can just be provided the answer. Also, this is actually the approach taken in MetaMath 0, which ended up with a very fast proof checker. They sort of pre-feed it tables with all the terms that it'll ever need to deal with, hints step by step of how to do any unifications or whatever that's going on and all of that. So within the stuff we've been talking about what the proof rules look like, we can make at least a few steps towards this approach. So rather than directly writing like that term A implies B as an argument to a relation, we can say, okay, the argument needs to be a single number, add extra parameters, which are going to be the names of any non-trivial term. So it's not A implies B, we're going to say T. If T is proved, and A is proved, and B is proved. And then we're going to have a separate hypothesis for this work of checking that T really is an implication between A and B. So again, this is kind of messy looking, but also a fairly mechanical transformation. Just take all of your expressions and kind of lift them out step by step, naming all the subterms and having explicit hypotheses for checking the shape instead of expecting to get the whole thing in one go. So a slightly larger example is this substitution on the implication rule. So again, you see there's just two terms in the conclusion that have like syntax in them. So we give them names, T2 and T1. Add new hypotheses checking that there's the expected shape. So it's not too complicated in any individual step. It just kind of flattens the structure down. But so now we've ended up with all of our original rules being in this form of fixed relations over fixed size numbers that the ZK proof systems will be happy to handle. But the one thing is, where are we getting these new facts from? So now if you, probably the most related prior work would be, there's some people that use like data log for analyzing programs. We have to do a very similar kind of relational transformation of things. And in that kind of setting, the idea is that you would pre-populate a table saying what the shape of all these terms are. You'd pick some ID, say, which things are which constructors, or have which forms. But we need to populate these facts. And then I guess the first approach we're going with, just to kind of not go too far from the design, not to add a completely new construct, we're going to say, okay, we're going to get these facts also from instances of extra proof rules. So we have this kind of axiom looking thing that says, hey, I'm declaring term T to be the implication between A and B. So this rule is a bit too simple, but look at what goes wrong and try to fix it. So one thing is that A and B can just be completely random numbers that have no interpretation as a term. Well, that might not actually be bad. Maybe it's just sort of acting like a opaque term. Worse, nothing stopping it from being a cycle. Your logic probably doesn't want to have cyclic terms like that, although some logicians do that, but yeah, not the logic you're trying to define probably. And then, but the worst thing is that nothing is stopping you from making conflicting definitions. Especially you can define it as something provable. Define term one to be A implies A, and you go prove A implies A, and you also define term one is A implies B, and then, well, term one is proved, so you can use that. So now the first thing about stopping cyclic terms and maybe unknown terms is the easier thing. We just have make a new judgment that says, hey, this number is known to be a well-defined term, and we use the depth arguments, as we already did to stop your main logical derivations from being cyclic. So now each of these terms that's defining a term, emitting a constructor, just has a conclusion saying, emits two conclusions, which is the first time we've seen that, but I mean, it doesn't really break any of the rest of the framework. Just, either of them is available to satisfy hypotheses elsewhere. So now, along with your specific shape telling you, okay, what constructor is term T made from, you also just say, hey, it's well-defined, and here's its depth. But this did not prevent you from making conflicting definitions, and to deal with that, we'll need to actually add a new kind of primitive mechanism to the rule definitions. And the thing is to just say that certain outputs are unique, or I mean, it really doesn't even have to interact with the ordinary hypothesis, so it's just a sort of unique tag to things. So the idea is that there's a special thing that you write it by the conclusions, but it's not necessarily a conclusion itself that says something is unique. And then when you're checking the proof, you need to check not just that the rules are well formed and all of the hypotheses are satisfied. You also need to check that there's no duplicates of these unique things. And then this can be enforced with the permutation argument. You gather up all these tags sorted by sorted by the tag and then sorted by the number, and make sure that no neighbors are equal. And then also, yes, if you're having if you have other kinds of constructors of your term, maybe you have like conjunction terms or something, you'd have a rule that would say that the new term being defined T, like maybe is a conjunction instead of T as an implication, but they would all still say, it's a well-defined term, and I'm defining a term. Yes, another thing to note is that we didn't want the depth argument here, because you don't want to say that term T means one thing with one depth and another thing with another. That would just let you make conflicting definitions again. But yeah, so now that we've got this machinery of having these unique things so that you can flatten the terms, you can make a pretty mechanical transformation of ordinary proof rules into something that's more friendly for zero-knowledge proofs. So each rule has parameters, has hypotheses, conclusions, optionally a unique output. I guess I didn't talk about what's public. So, ZK things usually have the notion of public data and the private part of the witness. So here, a natural thing to do seemed to be just to say that certain of the steps of the proof are public. And then further, you might want to say that there are certain rules that are only allowed to be used in the public part. So like here, we've got a rule that just asserts a new statement as an axiom, which is fine if that's a known part of your definition, used publicly, all your clients are expecting it. Not okay as part of the secret proof that your code's secure or whatever. So you have this little feature that you can tag rules to only be used as part of the public data. And then the question is how exactly you check this. And so here there's multiple approaches, and I can describe the way we did it, but there's other things we've thought of and other approaches you might have in mind. But basically, we're going for the approach of making dedicated circuits for the individual rules, like translated to circom. And you make a circuit for checking a bigger proof that has a bunch of copies of the rule circuit. You disable the excess copies you don't need. And then we figured out a way of using multiple instances of a circuit together. So I guess I think the important things of any design are that you don't want to have to generate a fresh circuit for a larger proof. Certainly not if you're doing something with the trusted setup, but even with the more scalable thing, maybe there's client-side computation or whatever. And then the other thing is whether you're trying to design a system for checking a specific logic, a specific set of proof rules, or something a little more general that somehow reads a description of the logic and processes it. And we have some ideas about how to do the more general thing, especially on like a SNARK style transcript, sort of making something kind of like a stripped down ZK VM that doesn't have general purpose control flow and general purpose memory and that sort of thing. But I think the making the dedicated circuits is probably going to be more efficient. So that's what we started with. And then the other thing is that to use a single fixed circuit or machine, or I don't know, not sure there's a general term, but to have a single definition that covers any size of proof. So we wanted to use something like recursion, but then again, we know with R1CS families and with circuits, there's these folding schemes where it's lighter weight on the prover and verifier. And with the SNARK systems, it seems like people only do full recursion of completely checking, having a circuit that completely checks another ZK proof, which yeah, seemed like a more complicated way to go. So anyways, that's the background, but the basic idea is to translate the rules to a subcircuit that implements those rules. And the only thing going on here that's super specific to the form of the rule is taking the parameters and outputting the different tuples that are the hypotheses and conclusions. And then you feed them into the lookup argument, and so there's a big sum or product, and you can rearrange the terms of that sum and product, so both the definitions from the conclusions and the lookup from the hypotheses can all be boiled down into one single number, which is the output of the, what's the effect of this rule on the claims. And then also you can disable this rule if you, just by having it output the identity. So then, this way, if you're having just one fixed hardwired circuit, you need to pick in advance, hey, I'm going to put 1,000 modus ponens step in one copy of the circuit. Maybe you don't need them all. So you can turn some off. Okay. Yeah, I guess we don't really need to review the exact formulas here. Yeah, I guess the one thing is that the tuples are coded as a polynomial like that, so the trailing zeros just drop out, and if you're hard coding a circuit for a specific rule where it knows that will always be a trailing zero, you don't need to put any gates in there for that. And then also for the lookup argument, we're working in particular with the logup argument, where everything is just additive, and the multiplicity is handled just by multiplying something by the count of how many times this is being used, rather than needing to have like a longer array where you physically put extra copies of it. Okay, right. Then to add the uniqueness, then there's an additional tuple or outputs from the circuit, and you do some extra local math to make a second number, which is the accumulator for the permutation argument, and then in the overall circuit, there will be a second chunk of it, which is like a big list, which is the second sorted version of the list, which is fed into the permutation argument and compared with the uniqueness from there, and also has the local constraints that do the sorting and no duplicates thing. So in the overall, you get a circuit, what we call a segment circuit, that has room for a bunch of rules, and it has all these sort of private inputs, but not necessarily private, but all these local inputs, and then the only thing you really need to know to check if it's like well behaved is these single numbers that are coming out from the accumulators, and you need to make sure that your Fiat-Shamir parameters are behaving themselves. Because once you have this small public interface, then you can have many segment circuits sitting next to each other and just add or combine the accumulators across them, make sure they're using the same randomness, and then you can check that the inputs to this whole collection of circuits together form a single valid proof. So yeah, and we're using in particular these folding arguments where you can take a bunch of instances of the circuit, and you don't need to do a full SNARK. You do little more than a vector commitment to your witnesses, and then combine all those together to get a single instance of something about the same size of the starting problem. Such that then you need to do one final SNARK of that final instance, and you need to know that the folding was done properly, and then you know that all of the instances were individually well behaved. Yeah, so basically you have the public outputs of the circuit, the Fiat-Shamir parameters, the accumulators, and then the vector commitments to the witness. Then also to do the Fiat-Shamir thing at all, we break the, we just treat the witness as two halves, the pre-randomization part and the remaining ones. We compute a separate vector commitment to the pre-randomization stuff and use a hash over that to generate the Fiat-Shamir parameters. Yeah, so you can compute like in the leaves, take a hash over the vector commitment, build a Merkle tree as you're grouping them up. And then at the root of this combination, you draw the actual parameters, which, so you needed to compute, so you need the entire proof to set this up. You compute the pre-Fiat-Shamir inputs everywhere, commit to those, hash them up, come up with these random parameters that will be used for the randomness, then fill in the rest of the parameters and then fold it together. This is another thing that seems to be pretty unavoidable, that if you're doing these polynomial lookup or permutation arguments, you really need the entire lists of input to be fixed in advance before you generate the Fiat-Shamir parameters, because it's just, the security is entirely based on this idea that drawing a random number is very unlikely to hit a root of a polynomial, unless the polynomial is 0. But if you know the polynomial before you pick, then you know, it's easy to engineer a collision. So it's seems difficult to not require preparing some things in advance. But still, it's just the input vector, so all this heavy cryptographic work of taking the vector commitment and some of the folding and things can be done in parallel on the segments. Yeah, so then to pack this entire thing as a SNARK, so the folding process itself just uses these small bits of data, which are the you know, the vector commitments and some of those public numbers about how the segments connect to each other. So the folding process itself only manipulates these small numbers, and then the prover is carrying along. The prover is carrying along the witnesses, but to know that the small commitment to the result was folded properly, you only need to work with the small bits. So then these are, you know, in practice, maybe even small enough to just send the list of everything, and that's how we initially are testing it. But you know, also you could have a SNARK of the folding process. Oh, I see. I'm moving a little too far. Okay. Right, so what you'd like to end up with a constant size result is to have a single SNARK saying that, hey, these parameters came from some set of coherent looking leafs, you know, whatever they are. And the user doesn't care how big the proof was, they don't care how many leafs they were, they just care that there were some, you know, consistent segments that together make up a proof. You could have a SNARK of the folding process, and then you need a second SNARK that the prover has this combined witness to the folded instance that, so here they're doing a full SNARK that they actually know a witness that satisfies the property, not the lighter folding thing. But then by doing that one final SNARK, you know, you convince people that the prover had the witness all along. So here's the overall design for how you get to a constant size SNARK of scalable proofs. All right. Yeah, this is the approach that we've been implementing using, for simplicity, just the NOVA folding scheme, not the IVC scheme, just the pure folding part. Yeah. But then I think also the ideas about simplifying the form of your rules are more general, and you might imagine like a, I don't know, data parallel GKR evaluation or some other kind of backend. All right, well, I think that's about as much detail as I necessarily wanted to get into without further questions, so.
Quick question.
Can you get a microphone?
hello. Is it on? Okay. Yeah, just a curiosity. So you show that in a Hilbert-style formal system. Just wondering which formal systems have you implemented? You know, whether you also even maybe implemented, I don't know, let's say the Isabelle Hall logic or something. Over, you know, just
we haven't gotten quite that fancy. We have a fancier propositional logic. It's based, you know, on this metavariable substitution stuff for metamath. The other thing we've done, we implemented rules for resolution. So just sort of, so these rules are more about, you know, searching through the clause lists to find where the variables are. That's, I guess that's what we have the most concrete evaluation. So there's just dedicated ZK unsat system for making unsat proofs. And it's a little bit of a odd comparison because they're actually using an interactive ZK proof system, one of these vol vector oblivious linear something evaluation, I think. Yeah, so our preliminary result, at least, is that we're like a little bit slower, but not even twice as slow, and sort of unclear how much speed up they're supposed to be getting from being interactive. I mean, some of the papers say numbers as high as like 30 times faster than a non-interactive SNARK, but a little unclear. Then also there's lots of ideas for optimizing what we're doing. You know, there's like known entries in these witness vectors that are small field elements compared to arbitrary field elements. You can do the, I guess we're you know, using these multiscalar multiplications for the commitments. So yeah, it's still very preliminary. But yeah, resolution proof system is, I guess, the other very different sort of logic that we've got.